Okay, thanks for investing your private time into the physical chemistry. In some sense, because of the specific attendance, this is actually a waste of time because it is very much targeting the project of Amelia and partially the project by John. But for you guys, it will be more like entertainment, and maybe they will watch the recording. So, who we are and what we are doing in this class, we look for wave in nature, originally electronic, but now all other forms of motion, because we want to predict outcome of instrumental measurements in chemistry and materials. And we completed many methods and free space boxes for different size start with oscillates, and now we go to rotational motion, which is important for diatonic and gas molecules that rotate and have low frequency IR rotational vibration spectra. And the main problem of quantum theory was started from the hydrogen atom and other atoms, where rotation is unavoidable. So there will be a review of what we have accomplished last time. There will be completion of not the whole story, but main part of the rigid two-dimensional rotation related to Bohr model. And at the course, there will be connection with more details to rotational vibration experiment, which is most typical for physical chemistry class. Obviously, it's more connection to experiment rather than boring stuff. And last, it will be a specific comment which is important for John if you are watching this recording. So start set. So this one is a little piece of review. If we have negative electron rotating, circling around positive nuclei in a circular orbit, which is an approximation, it doesn't necessarily need to be circular, it doesn't need to be two-dimensional, but we have this length, angle, and we do have, how nice when we render on the closer screen. Maybe accumulate less miles on first steps, but and we did found that circle rotational motion can be quantified with an observable called angular momentum. Right? The quicker it observes, the heavier thing rotates, the higher the angular momentum. And if we apply it to the planar two-dimensional motion, it can be expressed as derivative over angle, which is just very attractive from mathematical point of view, right? Then we did Hamiltonian, which is we started from momentum in the arc length direction, and then did some manipulation by multiplying and dividing by radius, introduced a measure of inertia for rotational motion, and came to the Hamiltonian rotational motion. So second derivative over angle and constant inertia in the denominator. And then we decided to be tricky in that sense. We decided to avoid direct generalization of Hamiltonian, but use the property of commutation. If the operator commutes with Hamiltonian, then they share the same set of eigenstates. Instead of, and since Hamiltonian here is composed of this projection of angular momentum squared, then it must commute with this angular momentum itself. Therefore, instead of recognizing Hamiltonian, finding eigenstates of Hamiltonian, we are finding eigenstates of angular momentum, making a right T. So we do, there is nothing new. Keep flexing or tell them to test. Angular momentum operator, unknown wave function psi of phi. Phi is angle an eigenvalue. In specific, if we do dimensionless eigenvalue, then it's just the question we want to solve, which is solved by, as it should be done, for the differential equations. And we are getting the general solution is same as same functional form as plane wave in free space. So the exponential is imaginary power, and something is accumulating, is going forward in this power. There are two unknowns. The eigenvalue of angular momentum projection z is unknown, and this normalization constant is unknown. How can we get these two unknown things? When we were exposed to the, and I'm trying to speak a little quicker because it is not really thing. When we were exposed to the part of the box, and we already got general form of solution that we were missing constants, we were practicing boundary conditions. If it is not sufficient, we have another setting to normalization. So we should look other boundary conditions and can we practice normalization. For the boundary conditions, there are no boundaries for rotation because it keeps rotating. But the object that rotates after making full circle should return to itself. Any of you took inorganic chemistry? So you know group theory. So after making full rotation, it should reproduce itself, right? You were in the inorganic group for a time.
No.
Rogers?
Well, I was in the group, but I didn't learn inorganic.
Okay. Jungi?
No.
Inorganic?
No.
Okay. Be prepared. Group theory. Like if I'm making full rotation, I will be myself again. And if it is like instead of myself, it is a square, you rotate it by 90 degrees and it reproduces itself. So if the angle differs by full circle, the function should be absolutely the same. And this condition is a replacement for boundary conditions. So it's an additional degree of freedom to find these two constants. Done visualization. Normalization. If it is a good wave function, it should be normalized and also orthogonal to itself or to other wave functions with other numbers. So psi of phi star integrated from 0 to 2 pi. Right? It's defined not from minus to plus infinity, but only on the angle. And this should be equal to 1. Which means if we have this normalization constant squared, right? It is a new material, but it is not so important and not so cool. So keep relaxing. I'll bring your attention. There will be interesting and important things. Preserve your intellectual strengths for a couple of minutes of true concentration. So normalization constant. And here, because of conjugation, we have exponential revolving in opposite directions, so they cancel. And the integration here goes from 0 to 2 pi. Which means upon integration, we get just 2 pi, right? So 2 pi c squared. And then we can solve for c squared. Right? So such value, normalization constant should take such value that upon integration we get 2 pi. So if we set up as normalization constant as 1 over square root of 2 pi, then it will be good normalized wave function. So we have a little less uncertainty. Uncertainty not in quantum sense, but in mathematics. first we got functional form of the function with two unknown coefficients, constant up front and the power of exponential. We are done with the constant up front. The only remaining thing is the eigenvalue of angular momentum. How can we get it? And we already discussed it. It was pronounced within the last 5 minutes. I was speaking quicker than we usually do, maybe, and I was inviting you to lean back and not to listen to the phone. So it is even shown here on this slide. Yes. So if you try to plug in this expression into boundary conditions, there is a chance that it will be additional equation that will help to solve for that. Okay. Orange value, not super necessary, but recommended. So plugging in our wave function into here, so it will be same normalization factor, same functional form, same eigenvalue of angular projection, but the argument is different. The summation of arguments of exponential is equivalent to product of two exponentials with these different arguments. Okay? And then we can see that for the left and right there is a factor that one can guess. Very simple logic. Now we get an equation that has at least 1, 2, 3, 4 fundamental constants. So e to the power I to pi m equals 1. Can we say that it is always correct? No. Can we say that we hope to find specific values of m when it will be correct? I knew you could, each of you can just walk up to the stage and just close your slides and explain it. It's fairy tale for adults. How do we interpret the symbol 1 here? If you concentrate on it and meditate, what do you think when you see symbol 1? On the left and right part, do we have integers, reals, or complex numbers? Last one. Oh, well, left is real now, but formally it must be complex, because on the right we have complex. So exponential with imaginary power will be complex from time to time. So our left side should be interpreted as a complex number, which means 1 plus I times 0. Right? So real projection is 1, imaginary projection is 0. And this exponential is also, it's not one number, it's a complex number. It's a 2-dimensional point on a complex plane. And in order of two numbers being equal, they should have real parts equal and imaginary parts equal. So our old body Euler, right? Assign imaginary sign equals 1, real part equals 1, complex part equals 0. So we need to find such values of m so that cosine of 2 pi times this unknown number will be 1. And you need to find such values of m so that sine of 2 pi times m will be equal to 0. Simultaneously. When cosine equals 1. Like if m equals 0.136, will it match this equation? So what should be the value? Or if 0 is okay, can 1, 2, it's super. Actually, I should turn camera and demonstrate active learning. So cosine oscillates and it takes value 1 each full period. Sine takes value a little more frequent, but you need to both of them coincide. So basically it will be only each period, not half a period. So according to Alyssa, m is equal to 0, 1, 2, 3, and all integers. What if m equals minus 1? Can we prolongate this figure into minus 2 pi? We would be 1 again, right? So any positive numbers are natural, and when they take negative values, they're integers. Right? So any integer number. So this part is recommended for observation, and it is one of the few problems that can be solved. Exactly. There will be a couple more, but as far as you are ascending the level of complexity, there will be less and less problems that can be solved, or less and less problems that can be solved with small, with little effort. So under this is wave function of the rotational motion in 2 dimensions. Under an approximation style that the rotating object doesn't escape planar rotation, so planar, and the radius is not allowed to change, so it's rigid property. It is if our H2 molecule will be nailed by a rigid stick, which doesn't allow them to contract, then it will be correct. And when it is squeezed so that it can rotate only one, which is a little crazy, but it's a sacrifice for a simple solution. Later on, this solution will be part of more complicated problems, which there are a couple more things that I would like to invite you to discuss. And I don't know how to arrange them. They are of equal value. One, what would happen if the rotator is allowed to go out of phase? For quantum particles that have uncertainty, it's natural property. Another thing, what if the length is allowed to contract or expand? Another thing, next on the list is it applicable to energy levels of soft molecule that rotates and rotational vibration spectrum? Too long list. Another thing is degeneracy. Did we spoke about this concept before? So degenerate is not a characteristic of a person who was over virtues. It is energies of states. it's not the end of the presentation. I just exited the notes. So you have seen these images before, and you will see them once again when maybe in modified form when Amelia will be presenting her research project, because it's staged later. Right now, you have much stronger background to analyze and interpret these images rather than listening to music and observing some motion. What can we learn from it? M is definition of letter M is the same as on previous slides. So it's dimensionless quantum number, dimensionless eigenvalue of angular momentum. And this thicker line is circumference, and when it goes inside, its real part of the wave function is negative, like cosine and sine of this exponential. When it is outside of the circumference, it's positive. And in order to be a good, correct wave function that matches all our expectations and requirements, after making the full circle, it should come to the same value. So if the eigenvalue is integer, then it matches this condition. Other examples are provided in order to demonstrate what would happen if this condition is not fulfilled. Hypothetically, mathematically, as an experiment, we can plug in any value of m. But then, because it doesn't support the condition of repeating the same value after the full circle, it will be not steady state, it will be not eigenstate, it will not stand unchanged in time. It will be some noisy thing that will not sustain on a long period of time, not an eigenstate. Right? So the reason of this little movie is to show that if m has integer values, you have noticed the shape retains the same. It slightly shifts by phase, but it is the same. If it is something different, you see a lot of noisy motion. When things are beautiful, they're correct. When they're noisy, they're wrong. It's not mathematical, but in most cases it's correct. Okay. A concept of degeneracy. So I am already appreciative of you participating in discussion, and specifically thanks to Alisa for suggesting integer numbers 0, 1, 2, 0, 1, 2. But we can have the -1, -2 as well. And what is specific? What is specific? What is interesting to focus at? That if it has quantum number of the same absolute value but different sign, the energy will be the same. So I'm jumping a little ahead of straight logic. Let's go back. We do have wave function. We do have a Hamiltonian, and we do have a protocol to find the energy of quantum state if we do know the wave function. So it is a procedure of this brand. So we put Hamiltonian in the middle and the wave function, the same wave function at the left and right. When we have this angular brackets, it means integration over angle. I'm skipping some simple math, but hope it will not progress because this Hamiltonian is just a second derivative over m, right? If you take one derivative over exponential, m goes up front as a constant. Right? If you take derivative once again, m goes up front once again. So it will be m squared. And imaginary units will compensate each other. So when you apply this as second derivative, and you get m squared. And then you get wave function from the other side and integrate, and they cancel each other. And the only thing is left will be Planck constant m's value of eigenvalue. Value of eigenvalue divided by inertia, right? Okay, and now I return back to the fact we were looking at in this figure. What is the property of m squared function? Is it even or odd? Even means symmetric. No matter positive or negative, it will be the same value. So no matter whether it rotates forwards or backwards, if the amplitude is the same, the energy will be the same. So this is the value of this quantum number. On this axis is energy. 0 provides 0, 1 provides 1, 2 provides 4, and then there is no doubts about m squared function. But it is interesting that for all values of m except 0, there are two values of angular momentum that provide the same energy. Right? So through your own effort, through following this effort, you discover that each energy state is W degenerate. Right? Under two conditions. It is a planar and it is rigid rotation. In some sense, at this point, we lose the chance to rigorously follow all equations. We can do it, but it will be needed to make this course for 2 semesters. Let me show what would happen if we abandon one of our approximations. So, right now, before this meeting, we were thinking about rotation in a plane. Therefore, angular momentum, which is vector, was oriented only in one direction, had only z projection. Right? Generally, it was only our approximation. There are no theorems that rotation will keep rotating in one plane. If you throw some object, it will rotate in all angles. So the angular momentum vector will perform some motion as well. This means that in addition to quantum number corresponding to rotation on our main plane, there should be another quantum number corresponding to rotations out of plane. So our favorite quantum number is m, our disfavorable quantum number is L for going out of plane. If one carefully, and they are called, you have seen these numbers, magnetic and orbital hydrogen. So what we've learned was magnetic planar motion. And the overall out of plane is orbital. So if you would repeat everything carefully, which I suggest we skip, and repeat the last procedure of finding energies of Hamiltonian. And we will also divide it by this constant inertia, to have them dimensionless. Then, before we had m squared, quantum number squared. Here, if one does it carefully, full picture or more precise picture, one would get not m squared but another quantum number, and it is not squared but L times L plus 1. Another property that I regret to declare instead of deriving. Here, I think I'll just squeeze the derivation, but this here not possible. The magnetic quantum number is still present. And the overall picture of dimensionless energy as function of angular quantum numbers will look similar. Parabola is something that looks almost like a square. But due to presence of two quantum numbers, there will be more states. And some of the larger number of states will coincide in energy. Do you remember when we did two-dimensional box? Right? We did a plane with kx and ky, and put quantum states as points on a plane. And then we did like a stripe or circle that covers number of states, density of states. So if our system has two quantum numbers, if it is, then space of states will be like plane, points spread over the space. And in this sense, in addition to points on the parabola, there will be points inside the parabola. The restrictions for allowed values of magnetic quantum number will be that must be less between L, right? So first we tell how much overall rotational energy is stored, and then we can decompose it over different forms of rotation, in plane and out. So when overall quantum rotation has a certain value, there are values of magnetic quantum number in between. So in this sense, the degeneracy number of states with certain energy will be different. In a sense of energies, the rigid planar rotor and rigid three-dimensional rotator will have same or very similar spectrum of energies. But in sense of degeneracy, it will be the main correction. So permission for a system to rotate out plane provides an update to degeneracy. Update to degeneracy. Okay, now we are going from rigorous mathematical derivations to fairy tale style. So it is what is typically expected from undergraduate courses. Just show pictures of stories. You already know how the wave function looks for rigid two-dimensional order. We saw this more. How the wave function will look if we allow the rotator to go out of plane. What will be the shape of the wave function? What will be independent? What will be independent variables? So we still have the rotation in x and y plane, And we have another angle that would correspond to rotation out of. The quicker the rotation, the larger the number of nodal points or nodal planes. If the rotator rotates around circumference only, the nodal planes will be arranged only in this plane. If it doesn't rotate in this direction, in this phi angle, and it rotates only out of plane, then there will be nodal planes in this other spatial regions. So this example corresponds to rotational motion only out of plane. So if we look along phi azimuthal angle, there are no nodal planes. It's like one donut, another donut, but they are continuous. If you look out of plane, there are 1, 2, 3, 4, 5 lobes, and between them 1, 2, 3, 4 nodes. So it's like fixed m equals not another L equals 5. Like that. Let's look on more examples, just to get a general idea. So now we have 1, 2, 3, 4 lobes, and in the out of space, out of plane direction. But in addition, there is one nodal line in the azimuthal motion. So it means it will move not only out of plane, but also in plane. So by looking on these figures, one can figure out what are the quantum numbers. And we are simplifying picture just to get the overall idea. This image has only less lobes in out of plane and more in the in plane. So overall amount of energy is the same, but it is redistributed between in plane and out of plane rotation. Less out of plane, more in plane. And ultimately, no out of plane, all in plane. Then it looks like a little flower. This 1, 2, 3, 4, 5, 6, 7, 8 patterns. And this colors can be probably explained by this. Everyone is sure. I have no doubt. Positive and negative. When we have one dimension, cosine was positive and negative, and if it is something more complicated, we do it as isosurfaces, and we need to signify positive and negative. And it is good. So now they all are the same. So it is our friends from several previous slides. So all rotations are in plane, less in plane, more out of plane, and then we progress to the. Can you interpret this image and describe it on your own? Like if some of you would call it to the stage and present the slides instead of me, which I have no doubts if each of you can. Just think for a few seconds. How would you explain this slide?
It's like, you must like say it.
Huh?
You must like say it or just.
Yeah, say it, please.
It's like SBD.
Sure. Repeat it for the camera.
From bottom to top, it's SPDFG orbitals.
Super. Absolutely.
Just at different angles.
Yes. So, and the difference in S, P, D, F, G orbitals is amount of rotation, right? if you have S orbital, there is no rotation. If there is a P orbital, there is a minimal amount of rotation, and it is 3 degenerate, right? 3 P orbitals. If it is D orbitals, it rotates quicker, and there are 5. So it's 1, 3, 5, 7, 9. So 2 M plus 1. Or M can be 0, 1, 2, 3. You know this particular. But it would come from solution of Schrödinger equation for a taper. It's just a little heavier than you want. It's not. You switch the mode and we run. I just found it on YouTube as illustration of the same figure for entertainment. So what it does, it illustrates the principle of rotation. The higher the magnetic quantum number, the quicker is rotation is in play. And for different values, it rotates forwards and backwards. So 1, 3, 5, 7. Degeneracy numbers for 3-dimensional rotations. And if we want to be meticulous, organized, we can put it in a table. So angular momentum, degeneracy, S, T, D, F. Right? What else can we look out of it? If we carefully plug in values of these states as proportional L plus 1. So suppose we practice this equation, and then it will be 0, 2, 6, 12, a little bit different from pure quadratic function. Then one can do a little exercise to find an offset of energies between two nearest neighbors. And in the remaining 3 minutes, I want to avoid us losing focus and provide motivation. Why we are doing one more effort of concentrating on this. This will be a connection to rotation vibrational spectrum. So because transitions occur between different levels, we need to know their differences. The differences between energies of levels will give peaks in the spectrum. And since energies of the levels are not arbitrary, they are precisely known with equation, we can plug in L plus 1 and L and do a little math. Right? So it turns out that subtracting these two quadratic functions, the energy offset will grow linearly. You can do it. You can prove it. So energy offset will grow linearly as function of 2, 4, 6, 8. Okay. And we are not yet ready to observe this equation in details. I hope to do it later. Brief overview of spectroscopy. How to compute spectrum, which means intensity as function of energy, response of system as frequency of the electromagnetic radiation. So there should be resonance between incident frequency and levels. This should be matched. There should be a specific condition for occupations. If both are empty and both are occupied, there will be no transition. And there should be some energy of interaction between light and matter. If all things are matched and we go over all initial and final, one will get frequency. So also one needs to put here the degeneracy of initial and final. So the information from this table is sufficient to reproduce the spectrum. So no vibrations, some vibrations. Transitions from one vibration to another, and at the same time from one rotational to another rotational state. The interaction between light and matter will offer here additional selection rule, but not every state can convert into each other. In Alyssa's previous slide, it was oscillator strength. But we noticed that energy differences between states are spread linearly as function of time. Therefore, these peaks here are offset by the same amount of energy. Good. So it's not the whole picture, it's only some how to say, overview of radiation vibration spectroscopy, but when you see it next time, maybe you will be more somewhat happy. Enough for today. Let's skip this special note for John because he is not here. Have a nice weekend, and I look forward to seeing you on Monday, and look forward to answering emails if there are any questions on projects.